darned. All this fiddling around. I guess I'm still not ready to take on that NC machine. Darn it, this is never gonna work. I've really had it now.
Too bad, but that's probably happened to everyone at some time or other.
Just can't go on like this. I'm gonna give it a try. Others have done it, and I'm smarter than they are. It can't be that hard.
And he's right, you know. You don't have to let things get so out of hand that sheer frustration forces you to turn to the NC machine. Modern NC machines are usually faster, even for less complex parts, and once you know how, easier to operate than conventional machines. Just what does the abbreviation NC stand for? NC means numerical control. In plain English, that's control by numbers. But today's modern NCs are really CNCs. Oh no, another abbreviation. It stands for Computer Numerical Control. That's the name for an NC machine working together with a computer. It can not only control, but also compute the data you type into it. We'll show you later on what it can do.
The NC machine doesn't look anything like the manually operated one. Oh well, at least it's got hand wheels, or I wouldn't even know how to move the darn thing.
Actually, you don't even need the hand wheels, because the machine moves automatically if you program it properly. But then that does make it look a little different from a conventional machine. The most noticeable difference is probably the control system, the CNC. It's the brains of the machine. It coordinates all the procedures you need to machine a workpiece. Of course, the control system can't turn a hand wheel. That's why there's a feed drive motor for each machine slide. One to move the cutter head, one to move the work table to the left or right, and one for up and down feed motions. The rotation of the motor is converted to longitudinal motion by a spindle and nut, so the control system can activate all machine movements. The control system transmits electrical signals to move the cutter or the workpiece. Since these signals are too weak to control the motor directly, they are amplified by a drive booster. The drive boosters are located in the control cabinet. You'll also find the programmable controller, or PC, there. Its job is to make sure that all the functions set in motion by the control system are really converted to electrical circuits. Each machine slide is equipped with a linear measuring system. This system emits electrical signals when the machine slide moves. The control system can tell by these signals how far the machine slide has moved. That's necessary because the control system can't see, of course, where the tool is at any given time. Now let's take a look at an operator working on a conventional machine. In simple terms, it looks something like this. He knows that the cutter is supposed to move, let's say, 100 millimeters. So he turns the hand wheel an appropriate distance, keeps an eye on the cutter, and checks to see if he has moved the tool far enough. He does that until he has moved the desired distance. While doing so, he constantly regulates the position of the cutter in relation to the workpiece. The NC machine does exactly the same thing. The control system gives the drive booster a command to move. The booster sets the feed motor in rotation. The machine slide begins to move. The linear measuring system signals the control system, for example, 1 millimeter moved. The control system checks to see if that's enough. If it is, it gives the signal motor stop. If not, it continues the procedure. But the entire procedure goes so fast that a position check, a comparison of set point and actual positions, is carried out every 1,000th of a millimeter. This whole process is called a position control loop.
Looks like that control system's a real clever gadget. Now, I can't wait to see what it's got in it. I want to see if it really works.
Seen from the outside, the control system can be divided into three major components: the video screen, monitor, the programming keyboard, and the machine control panel. The screen shows the operator the information he needs at all times. Actual values are shown in large display during machining operations. At least 2 complete blocks are displayed on screen when programming.
Well, it's always good to know what's going on.
Next, we have the keys for entering a program. There's a numeric keypad, address key array, and programmable function keys for making frequently repeated entries with a single press of a key. The last group are the keys for machine operations. From here, you can control all machine functions manually as well. Fortunately, we don't have to worry about what it looks like on the inside. You'll find roughly the following parts: the program store, the tool compensation store, the computer, and the input-output unit. Together, all this is called the control hardware.
Okay. Now I'm going to take a closer look. Yeah. Everything's there all right. Hand wheel? Good. Let's see what happens when I press something. Oh, damn, what was that?
Oh, well, it was probably a little too early for a trial operation. In shop talk, we call that a genuine collision. But no harm done, because the FPNCs have a built-in safety coupling on each axis drive. The worst that can happen in a crash like that is a damaged tool. The machine itself is safe. By the way, safety is a big word in NC machines for the protection of both the machine and the operator. There are limit switches at the end of the traverse paths on the machine slides, for instance. They stop the machine slides before they hit the mechanical limit stops. The operating space is fully enclosed, so you stay clean and safe while you're working.
An NC machine like this is a real fine thing, but there's something I've got to do too.
Before the machine can process a workpiece, a human has to tell it what it's supposed to do. The operator knows from the part drawing how the finished workpiece is supposed to look. That means he knows the geometric data. He also knows how the workpiece is supposed to be machined, so he knows the technological data too. If he also knows how to talk to the control system, he can enter these data into the control system in the form of a program. The control system uses this information to control the machine. NC machines can then be used to solve problems that cannot be solved with manually controlled machines. Milling inclined lines, for example, or circles without using a rotary table. To be able to program the control system, our operator will no doubt have to freshen up on a few basic geometric terms.
Well, I'll be damned. You mean I have to learn geometry now? I was even bad at that at school.
You really do need a few basic expressions from geometry in order to tell the control system what tool motions to carry out. Without them, the control system understands absolutely nothing at all. First of all, you give names to the machine motions. If the table moves to the left or right, we say that movement takes place on the x-axis. For the cutter head, we speak of the y-axis. And when the table moves up or down, we say that movement takes place on the z-axis. Of course, we don't only want to say what should move, but also where it should move. For instance, if we say x-axis to the left, this information is not very clear. On a column and knee type machine, the table will move. On a bed type machine, the cutter will move while the table remains stationary. So you would also have to say what component is supposed to move. In programming, however, that doesn't matter. The only thing of real interest here is which movement the tool should make in relation to the workpiece. Movement of the table to the right has the same effect as movement of the tool to the left. Upward movement of the table brings about the same results as downward movement of the tool. In programming, think in terms of the workpiece always being stationary while only the cutter moves. This way of looking at it is called relative tool motion. Once we agree on that, we can give names to the machine's traverse directions.
Okay, let me give it a try.
A relative tool movement to the right, table to the left, is called x plus. A relative tool movement to the left, table to the right, is x minus. Tool to the rear is y plus. To the front, y minus. Tool up, table down, z plus. Tool down, table up, z minus. To make this all easier to remember, there's the right-hand rule. When the middle finger is pointing in the direction of z plus, the index finger points to y plus, and the thumb to x plus.
All right, I understand that now. I even saw it move. But you haven't said anything about programming yet.
Yes, that's right, but x, y, and z are also used to identify the points on a workpiece, so the control system knows where it should move to. To do this, you position the axes x, y, and z on the workpiece in such a way that x and y define the points on the surface, and z is the downfeed depth. So just how does this function on the workpiece surface? The two axes form a two-dimensional coordinate system. The point of intersection is called the 0 point. If you apply a scale to the axes, you can define any point by indicating its x and y value.
That doesn't sound so hard. Now let me see if I can do this example.
The important thing in this example is to identify the center points of 3 boreholes with x and y coordinates. Now let's start by defining the coordinates. The hole at the upper left is 19 millimeters in the x direction and 55 millimeters in the y direction measured from the 0 point. So its coordinates are x19, y55. The hole at the bottom is 45 millimeters in the x direction and 15 millimeters in the y direction away from the 0 point. That makes its coordinates x45 and y15. The hole at the upper right is 70 millimeters in the x direction and 50 millimeters in the y direction measured from the 0 point. Its coordinates are x70 and y50.
That wasn't so hard after all.
You can locate the 0 point of the coordinate system anywhere you want. It depends on the dimensions of the drawing. It's usually located at the point on which most of the dimensions are based. In our example, that's the lower left-hand corner of the workpiece. Once you have defined it, this point is called the workpiece 0 point. It always remains the same for this workpiece and is identified by this symbol. In this example, most of the dimensions are based on the lower right-hand corner. So that's the best location for the workpiece 0 point. Up to now, we've only had to identify points on the x-axis to the right of the 0 point. Now our set point positions are located to the left of the 0 point, too. Coordinates located in an axis direction opposite the 0 point are given negative prefix signs. This point, for example, has the coordinates x minus 75 and y 5. Now let's see briefly how things look when we add the z-axis. Z coordinates are used to program downfeed depth. Z equals 0 is usually located on the workpiece surface, so that every downfeed movement has a negative prefix. In our example, we'll cut to the final depth, Z equals minus 10.
Okay, that's clear. But how does the control system know where my workpiece 0 point is?
To tell the control system where the workpiece 0 point is located, you move to the desired point on each axis with a zeroing tool or edge tracer. Select operating mode Set 0 Point and tell the control system for each axis, this is the 0 point. After that, the control system always knows the position of the workpiece within the machine's operating range. If the power fails, though, this 0 point assignment is lost. To help find the 0 point again if that happens, an additional permanent machine 0 point has been built in. It's called the machine reference 0 point. The control system knows this point and can find it again at any time. Before setting the 0 point, you'll need to move to the reference point and note how far you had to move in the Z, Y, and X directions in order to reach the 0 point. Then, if the power fails, you can go back to the reference point. From there, you know, of course, where the 0 point is located. There are 3 important locations to consider when programming a milling machine. The reference point, that's the 0 point of the machine's permanent coordinate system. The workpiece 0 point, which can be selected as desired but remains permanent for a given workpiece, and the program 0 point. Current data in the program are based on this point. It can be shifted during programming, but at the moment we don't have to concern ourselves with these details. For the time being, the program 0 point and the workpiece 0 point are identical. So, with the help of the coordinate system, you can clearly define all of the points on a workpiece. To cause the tool to move the way you want it to, you just indicate the X, Y, and Z values of the set point position based on the workpiece 0 point. If you want to move from P1 to P2, for example, program X50. That is exactly the distance from the 0 point to P2. To move from P2 to P3, program Y25, since P3 is located 25 millimeters from the 0 point. So you indicate the point to which the tool should move. This indication has nothing to do with the tool's current location. It's called an absolute dimension. Sometimes, however, the dimensions indicated in a part drawing are such that it might be easier to specify how far the tool should move away from its current location. In this case, the distance from P1 to P2 is still 50, because P2 is located 50 millimeters from P1 in the X direction. Getting to P3 from P2 is a different story. P3 is 30 millimeters from P2 and opposite the direction of the y-axis. So in this case, you'll have to program y minus 30. This method of indicating dimensions is called programming in chain dimensions or increments. Dimensions are based on the current position of the tool. You specify how far the tool should move. Let's summarize again. Absolute dimensions. All dimensions are based on the workpiece 0 point. You program where the tool should move. The programming command for this is G90. Chain dimensions. Dimensions are based on the endpoint of the previous dimension. In this case, you program how far you want the tool to move. The programming command is G91.
Darn, that's real complicated. I'm going to have to take a closer look at that. Now let's see. If I want to move to that point, it's 40 millimeters away from the 0 point in the x direction and 50 millimeters away in the y direction. Those are the absolute dimensions. And if I want to program it in chain dimensions, then I have to say move 20 millimeters in x and 30 millimeters in y. Okay, I've got it now. Now I can tell the control system where I want the tool to go, but that's not all there is to it, right?
Of course not. The control system also has to know how to get to that point, whether to follow a straight or circular path, what feed rate and spindle speed to move at, when to switch the coolant on and off, and so on. To give it this information, we use a language which was specifically developed for CNC control systems, the programming language. Like any other language, it is made up of words. Each word stands for a command given to the control system by the programmer. A word is made up of a code letter, the address, and a number of digits. S is the address of the spindle speed, for example. S1000 means spindle speed 1000 RPM. We're already familiar with G90. That's the word or command for absolute dimensions. And one more example. The address M, together with the digits 08, is the command for turning the coolant on. Words are roughly divided into 4 groups. The first group contains positioning commands with addresses X, Y, and Z. As we have already seen, these addresses are used to program the destination of a traversing movement. Group 2 contains path conditions with address G. G01, for instance, means move in a straight line, and G02 means move clockwise on a circular path to the destination.
I already know G90. That's the path condition for absolute dimensions. G91 is the path condition for chain dimensions.
The third group contains machine switching functions with address M. M08 means coolant on, for example. M09 means coolant off. The fourth group contains addresses for feed and spindle data. F is the address for the feed rate.
I already know address S, too. That's the one I use to program the spindle speed.
In addition to these, there are a few other addresses, but we don't need to deal with them at the moment. Several words are joined together to form a block. A block forms a complete set of operating instructions for the machine. Complete operating instructions for a traversing movement include, for example, what location the tool should move to, how to get to that location, and at which feed rate and spindle speed it should operate. Finally, a program consists of a number of blocks. The blocks are numbered in sequence. The address for the block number is N.
You know, that was a lot to take in. I guess I'm going to have to practice so I'll get it down pat after a while. But I got a pretty good idea how it works now. It's not as bad as I thought it was going to be.
If you've paid attention, you will now be familiar with the most important basic terms of NC technology. In part 2 of our film, we'll learn how to apply this knowledge to everyday workshop practice. there's good reason to be optimistic. We already know how an NC machine functions and everything we need for programming. But keeping to a fixed method of programming can be a big help, especially for someone who's new at NC machines. The best thing to do is to work step by step, one item at a time, as follows. Step 1. Selecting the workpiece 0 point. Set the 0 point at the location where most of the dimensions originate. Step 2. Defining the coordinates. Watch out, there's a difference between programming with absolute coordinates and incremental coordinates. Step 3. Working out a job plan. When programming, be sure not to forget anything, because it's hard to intervene once machining has already started. That's why the whole machining program is planned step by step from start to finish, including traverse paths, feed rate, spindle speed, tool, coolant, etc. Step 4, writing the program. The planned work steps must be translated into the machine language the control system understands. Step 5, entering the program. Now sit down at the control system and type in the program. With a little bit of practice, most programs can be generated directly on the control system. Step 6, testing the program. Before running the program, you should test it first, just to play it safe. There are several ways of doing this. For example, doing a test run without the tool, doing a graphic simulation on the video screen, or processing individual blocks. Step 7, running the program. Once everything is correct, push the start button and the control system and machine will take care of the rest. And now we'll try out a practical example. Let's take a simple groove to start out with. Step 1. Select the workpiece 0 point.
The workpiece 0 point is obvious. It's located at the lower left corner.
Step 2. Determine the coordinates.
It looks like the whole thing is in absolute dimensions, so defining coordinates is also really easy. The starting point is x15, y30. The depth is z minus 10. The end point of the groove is x65.
Now it's time for the next step. Step 3. Working out the machining plan.
Okay, that's pretty easy too. First, I make a quick move to a position above the starting point using the rapid traverse function. Then I downfeed at a feed rate of 50 and a speed of 200. Now I mill the groove at a feed rate of 200 and a speed of 500. Then I have to retract the cutter. And finally do a rapid exit from the workpiece. That's it. I'm finished. Okay, now it's time for me to write the program. In the first block, I have to move to above the starting point in rapid traverse. How do you program rapid rate?
Of course, there's also a command for programming the rapid rate, and that is G00, rapid traverse to the program target point.
That's fine with me, so all I have to do is type in G00. Okay, let's get going. Block number N0001, then G00 for rapid movement. My destination is X15 and Y30. Wait a minute, I gotta watch out that I don't mess up the workpiece. I'd better stay 2 millimeters above it. That'll be Z2.
This command is already complete because feed and spindle aren't needed with rapid traverse.
The next thing I have to do is downfeed.
The downfeed movement is on the Z-axis on a straight line in feed mode.
That will be block number 2. Of course, I'm not going to do it in rapid traverse. I can do it at the feed rate. Just keep going in a straight line. Moving in a straight line in feed mode. That was path condition G01. Where to? Yeah, to Z minus 10. X and Y stay the same.
Axes do not have to be programmed if there aren't any movements along them.
But this time around, I have to program a feed rate and a spindle speed. The feed rate is F50 millimeters per minute. The spindle speed is S200 RPM. That was block number 2. Now it's high time to cut the groove. This is going to be block number 3. Milling is, of course, something I can do in feed mode. In other words, G01.
The command doesn't have to be repeated. It is valid up to the point where a new path condition is programmed.
All right, then I don't have to type it out. Great, I found a shortcut. Now what? Where do I want to go? You bet, X65. Y stays the same, and the depth doesn't change either. But one thing I have to do is make the feed rate higher, and that'll be F200 millimeters per minute. And I'll need a higher spindle speed, too. That'll be S500 RPM. Okay, now I have to get the tool back out of the groove and a little bit above the workpiece. Now on to block number 4. I move in a straight line again. G01 is still in effect. I move to Z2. And now I get away from the workpiece. That'll be block number 5. Back to rapid traverse, meaning G00, to X200 and Z200. Okay, that's it.
Hey, hang on, not yet. The control system still doesn't know that was the end of the program. You tell it that with command M30.
Well, so much for block number 6, M30. That's it for now.
Now we're really through. We've just finished writing our first complete program.
Let's give it a go on the machine.
To input the program, you first have to select the appropriate operating mode. Then type in the program block for block. Each entry must be confirmed by sending it off with the Enter key. Once all the blocks have been passed on to the control system, machining can begin.
Now what? Gotta move to the reference point. Define the workpiece 0 point. All right, that's where it goes. Define 0 everywhere it's supposed to be. Now let's see what happens. Hey, great. Works like a charm.
Sure, that program was easy. But the NC machine can handle really long and complicated programs too, with just the same degree of precision.
Now I'm going to try my luck on another piece. Let's see how I do. If I got to go from here to there, my tool has to be there. Now, wait a sec. The tool ought to be there and then go up to there. Now what am I supposed to program? Now don't tell me I have to figure out all the points. You gotta be kidding.
No, that's ancient history. In the old days, if you wanted to cut a 50-millimeter edge using a manually operated machine, you had to account for the tool radius manually. The tool radius had to be added at the beginning and at the end of the traverse. The traverse path had to be longer than the edge to be milled by 2 times R. With old-fashioned control systems, all of this had to be calculated too. Nowadays, this is done automatically by contour control. All the operator has to do is program the contour. The actual tool path is figured out by the control system. Of course, it can't do this unless it knows what the tool specifications are. To enable a program to work with different tools, tool data aren't contained in the program, but rather in a separate memory, the tool compensation register for the particular tool. The program itself only contains the number under which the compensation value is stored. Before starting to run a program, the user enters the data for the tool he is using under the appropriate number in the compensation data register. This won't change the program. It stays just the way it was. To end up with the programmed contour when milling, the center point or axis of the cutter must be guided along a path with the same spacing from the tool as the tool radius. This is called an equidistant path. When this is programmed properly, the control system calculates all the points of intersection for the individual tool paths. If desired, it inserts blends at irregular contour transitions. For the control system to do this, it must be told whether the tool is to the left or right of the contour in respect of the milling direction before moving to the contour. This is handled by 2 programming commands. G41, tool is to the left of the contour. G42, tool is to the right of the contour. These 2 commands tell the control system that from now on it is supposed to calculate the cutter path. That means start so-called contour compensation. Further input is prompted by dialog. That means the control system automatically requests further entries from the user.
If everything is automatic, then I have time to check what the manual says about the control system. Ow! That's what comes from all this studying. First, I need operating mode 11 for program input, and then a block number. Now G41, and then the letters DG. What the devil does that mean?
DG is the way the control system asks for the compensation number. This compensation number indicates under which number the compensation value, that is the radius of the cutter being used, is stored in the tool register.
Okay, so I'll type whatever I feel like. Right now, it doesn't matter what. Now I see a G4. What does that mean?
The control system wants to know how to approach the contour. To keep from damaging the contour during the move, the tool has to approach the contour tangentially. There are 3 ways of doing this on the control system. Moving in parallel to the contour. To do this, use Command G45. Semicircular approach. To do this, use Command G46. Approach in a quarter circle. To do this, use Command G47.
Why don't I try putting in a 5 for G45? Now I got an A. What's that?
A simply stands for programming the spacing between the down feed point and the first contour point. In other words, if the user inputs this spacing to the control system, the system automatically calculates the required down feed point and then leads the tool along the desired path, approaching the contour tangentially.
Now I'll give it 10 millimeters.
X and Y are used to program the first contour point required.
Doesn't matter what number I put in, so I'll just enter any old thing. Aha! Now the control system wants another path condition.
Right. The control system wants to know if it's supposed to travel to the down feed point at rapid rate or at the feed rate along a straight line. So you tell it what to do using the path condition. Now the control system needs another specification defining tool contour control. There are 2 possibilities. G61, the control system inserts blends at irregular transition points. G60, the tool travels precisely to corners. The inner radius created in this way is equal to the tool radius. The last entry defines the contour feed. You have a choice between constant feed along the cutter axis, Command M62, constant feed along the tool edge, Command M60. That is, the feed rate at the inside corners is reduced and increased at the outside corners. Feed limitation at the outer corners, Command M61. That is, there's a slowdown at the inside corners but no speed up on the outside corners. That was just a complete block used to start contour compensation. Of course, tools of different lengths can be used in one program. For example, a roughing tool and a finishing tool. With the spindle nose in the same position, the tool tip can be in various positions. The difference in length must be compensated. Because if the workpiece 0 point, for example, is set using the finishing tool, the control system accurately notes the position of the spindle nose for Z equals 0. It always travels back to this position whenever Z equals 0 is programmed. If the roughing tool is longer, for example, the control system could possibly move the tool in rapid traverse and wind up hitting the workpiece. It has to stop before that happens. In other words, the position of the spindle nose in the direction Z plus must be corrected. The the compensation value is exactly equal to the difference in length. If a tool is shorter than the zero tool, the correction must be in the direction z minus. Well, now we know enough to try our hand at programming an outer contour.
With this example, we'll again be following our plan of attack. The first thing I always do is define the workpiece 0 point. I'll locate it at the lower left corner of the workpiece. Then I've got to determine the coordinates. I'm cutting to the right, so the tool is then to the left of the contour. Well, let me program the thing. Move over the workpiece. First the feed rate, spindle speed, etc. Now contour compensation starts. My tool is in the cutting direction to the left of the contour. The command was G41. Then I enter the compensation number. Now I've got to program how to travel to the contour. Here's a straight line. I'll simply move in parallel with the contour. That was G45. The downfeed point should be spaced 6 millimeters from the first contour point. That's A6. The first contour coordinate is X10, Y10. And the tool is supposed to traverse rapidly to the downfeed point. Therefore, I hit G00. I want blends, so it's G61. And the feed is supposed to remain constant, so M60. This is a really long block. But on the other hand, the control system does a lot of things for me automatically. Now I program the contour.
The control system recognizes that contour compensation is over when command G40 is given.
All right, G40. And then I move away again, parallel to the contour to a distance of 3 millimeters. Now the last thing to do is to move away from the workpiece in rapid traverse mode. And that's the end of the program. Can't wait to find out if it was right. Uh-oh, here we go again. First, I define the workpiece 0 point. Now I have to enter the tool radius.
Tool compensations are entered in mode 10. Just call up the number you want and enter the radius.
All right. And now? Hey, that's great. It really worked. I'm starting to get to like this machine. Couldn't have done a better job myself.
But let's not be fooled by one success. Don't forget that we had all this trouble because we messed up a circular arc at the beginning.
Here it is, milling circles.
There are two different path conditions for milling circles. Clockwise with G02 counterclockwise with G03. Furthermore, the control system needs the coordinates of the destination, and it has to know where the center point of the circle is. Address I indicates how far you have to go from the starting point in the X direction in order to get to the center of the circle. Address J indicates how far you have to go on Y to get to the center. So the center point of the circle is programmed in incremental dimensions relative to the starting point of the circle. Okay, let's look at an example. Here you would have to go 20 millimeters in the X direction and 28 millimeters in the Y direction to travel to the center. So you program I 20 and J minus 28. And now we'll turn to the problem you couldn't solve in a conventional manner.
Okay, now I'll try an NC approach. Here we go. Select the workpiece 0 point, traverse the workpiece, downfeed, contour compensation on, to the left of the workpiece, into the program, and so on. Well, get a load of that. It sure does make a difference.
Naturally, the NC machine has a whole lot of other features we haven't dealt with here. These include milling cycles, boring or drilling cycles, mirror imaging, rounding corners, beveling, and milling helixes. Your operator's manual contains detailed instructions on how to make the most of all these options. And don't forget, once you give it a try, you'll find it's a lot easier than you thought.